So, today's experiment. What is our experiment? It's about batch sterilization, right? So, during batch sterilization process, there are three stages. What are those three stages? Heating period, holding period, and cooling period. Okay. Determining the holding time is our experiment. So, you finding out the heating period and cooling period, and then finding out the holding period, that is our experiment. So the design criteria for batch sterilization, we are giving it with a del factor. So what is the del factor? So during the steam sterilization, how much of the microorganism have been reduced from its initial count? Okay, so that is given by del factor. Del factor is otherwise known as nebula factor, and that is denoted by del factor is equal to ln n0 by nt. Okay, so first we need to determine the overall del factor. That means after going through these all three stages, the amount of microorganism that should be reduced should be defined before the experiment itself. Okay, so mostly we are taking that nebula factor based upon the initial number of microorganisms and the final number of microorganisms. The initial number of microorganisms we need to count like for the design purpose we are taking it like a 10 to the power 11 initial number of cells are present. And for this study generally we will be having a model microorganism. And what is that model microorganism that we are using? Geobacillus stereothermophilus, which is a thermophilic bacteria which is supposed to survive even at a very high temperature. Okay, so if you are finding out the holding time for that particular microorganism, all other microorganisms will be naturally reduced, naturally killed. Okay, so as the purpose of our experiment is to determine the holding time, this holding time is dependent upon the del factor by the equation del is equal to k into t, where k is the depth rate constant. Okay, so we need to find out the t. Okay, so and this k is again dependent upon the temperature. So when the temperature changes, the k value also will change. So depth rate will increase as the temperature is raised. So our aim is to find out this holding time by actually finding out what is the del factor during that holding time. Okay, so del factor for the heating and the cooling time can be actually determined using the experiment, and del overall, which is previously determined. So if the initial number of microorganisms is 10 to the power 11, I need to finally conclude what is the final number of microorganism also. The final number of microorganism that we can take like a 10 to the power minus 3, meaning that the physical meaning of this is if you are doing the batch sterilization experiment 1000 times, one bacteria can survive. Okay, that is called 10 to the power minus 3. Using this, del overall is now calculated. So del overall is ln n0 by nt. Now in our case it will be coming around 32.2 or something like that. Okay, so this is the overall del factor which is achieved through these three stages. What are those three stages? Heating period, holding period, and cooling period. Okay, so del during the heating period and del during the cooling period I am calculating. From this, del holding can be determined. Because del holding is equal to del overall minus del heating minus del cooling. Okay, so we can actually find out what is del factor during the holding time. From our equation, previous equation, del is equal to k into t, I can calculate the holding time. So this is our experiment. Okay, as I said, del is equal to k into t, where k is the specific depth rate constant, and this depth rate constant is dependent upon again on temperature. So when the temperature is increased, this depth rate constant also increases by as per the Arrhenius equation. K is equal to a e power minus ea by rt. Okay, so the activation energy and the Arrhenius constant of that particular bacteria was previously determined in our previous experiment. For Geobacillus stereothermophilus is the model microorganism that we are using. So for that particular microorganism, we need to first define what is the Arrhenius constant and the activation energy during the thermal depth rate kinetics of that particular microorganism. Okay, so in our experiment, as I said, I am just calculating what is del heating and del cooling. From that, using the previous data, I'm just calculating the holding time which is required for killing of model microorganism. The model microorganism is the thermophilic bacteria. Okay, so we are having a batch sterilization unit. So the batch sterilization unit is having in situ sterilization in that, meaning that the sterilization, so reactor itself consists of the sterilization part. So we are having a heating rod for to heat, in order to heat the media that is present. For our experiment, we are simply using distilled water inside. We are just switching on the fermenter. The temperature will be noted down, okay, at the different time intervals. So for our microorganism, if you know the temperature, I can actually calculate Ka, because we determined the activation energy and Arrhenius constant for that particular microorganism. K is equal to A e power minus Ea by RT. Okay, so we are using an incremental method. Incremental method means the temperature is raised slowly. I'm just noting down at a particular interval of time. I'm noting down the temperature. Okay, so for that temperature, we will be calculating the K. So I am raising the temperature from the normal temperature to the sterilization temperature, which is 121 degrees Celsius. Okay, so what you need to do is use a stopwatch every time interval, take it like 2 minutes. So every 2 minutes, note down the temperature. Using that temperature data, I can actually calculate K. Okay, so until it reaches 121 degrees Celsius, you need to heat it. Okay, once that is over, when the temperature is 121 degrees Celsius, switch off the sterilization and note down the temperature until it comes to the normal temperature. See the sterilization panel in the control panel. So this is the control panel. So we can control the sterilization here. Okay. So what I need to, there is a knob for controlling the process of sterilization. So we need to switch on the sterilization and press this button. The sterilization now will be on. Okay. So you can see the current temperature like 35.6 degrees Celsius. What we need to do is every 2 minutes you need to note the temperature. So now I am switching it off. When you start the experiment, you can discontinue it. Okay. So every 2 minutes until it reaches 121 degrees Celsius, note down the temperature. Once that temperature is reached, we can switch off the sterilization and we can see the temperature now in the temperature panel. We are having another panel here. Okay. So from that 121 degrees Celsius to the normal temperature, you need to continue it. So this is our experiment. Just put the sterilization, switch on the sterilization button. So note down the temperature now, like for 0 minutes. Okay, so what is the temperature now? 35.6. Okay, now every 2 minutes note down the temperature. 2 minutes over. What is the temperature now? 45.9. Note it down. The heating cycle is about to over. So when it reaches 121 degrees Celsius, what we need to use? We need to switch off the sterilization. So we need to switch off the sterilization, put the process on. Now we can see the temperature on the another panel, that is the temperature panel. Okay. Okay. So there is a variation that have been showing between the sterilization panel and the temperature panel, the process panel. Okay. So you can take like the error term and reduce the temperature. Okay. So cooling period is going to be a slow process. So we can note down the temperature for every 5 minutes. Okay. So every 5 minutes, note down the temperature until it reaches like the normal temperature. So we have noted down the temperature at different time intervals, both for heating cycle and for the cooling cycle. Okay. So for each temperature, we are calculating the K value using the Arrhenius equation, like K is equal to A e power minus EA by RT. And once you know the K value, and for that particular temperature, I can calculate del value. So calculate for each temperature for the heating cycle, add it together. So we will be getting the summation of the del heating value. Do the same thing for the cooling cycle. So this is the del cooling. So as per the previous information, overall del for this batch sterilization is given by ln N0 by Nt, where N0 is the initial number of microorganisms that may be present and Nt is the final number of microorganisms. Both the values I am assuming like 10 to the power 11 and 10 to the power minus 3 respectively. As I said previously, 10 to the power minus 3 means in every 1000 batch sterilization, one cell can escape. So this value is 32.2. So after doing the batch sterilization, which consists of heating cycle, holding cycle and cooling cycle, the overall del factor should be 32.2. So from the calculated values, del overall is equal to del heating plus del cooling plus del holding. So from this equation, del holding is equal to del overall minus del heating minus del cooling. So that is 32.2 minus del heating is 14.82 and del cooling is 15.94. So that is, what is the answer? Check it. So that is 32.2 minus 30.31. And what is that? 1.93. So during holding, we are supposed to have a del value of 1.93. So already we know the equation, del holding is equal to K at the holding temperature. The holding temperature is 121 degrees Celsius into T holding. So T holding is the holding time. So from this, the holding time can be calculated as del holding divided by the K value at 121 degrees Celsius. For our model microorganism, the K value is 2.54 minute inverse. So del holding, which is 1.93, I need to divide it with the 2.54 and you will be getting the holding time as 0.759, approximately 0.76 minutes. So according to our calculation, our holding time is 0.76 minute. Okay. So that's all for a batch sterilization.